we physicists have held up 100 years, beginning around 1916, for this photograph. It is a locale where dim openings may, in all likelihood, be one of the most charming and clandestine quirks in the universe. They are colossal beasts in terms of power, but basically intangible to us. A dim opening, locking in, might be 2 to 4 million times the mass of the Sun. One of these, accordingly, of the assessment offered over the last years. We have gone from knowing, in a real sense, nothing about them to finding out progressively more, exceptionally close and personal. Remembering that things have absolutely gotten crazier. Kaku has announced that we finally got to really take a look at what is inside a dim opening. This new information reveals insights into nuances the universe of science could have missed from the outset. Join us as we dive deeper into dim openings and unveil what's inside. What are dim openings? Space is massive, but what are dim openings? Before we jump into the nuances of what Kaku found, we need to look at the basics. While most of us have some idea of what dim openings are, there are still gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of dim openings. At that time, the idea was entirely speculative. It took another 50 years for scientists to find evidence of their reality, which happened during the 1960s. Experts studying the Cygnus constellation observed an unusually bright blue star emitting X-rays. This star wasn't stationary. It was orbiting a massive dark object. Upon further examination, it became clear that the X-rays were being pulled into this object. Thus, the term dim opening, black hole, was born. This discovery was crucial because it showed that dim openings were not just a product of Einstein's imagination, but real entities in space that we needed to study. Scientists worldwide began to focus on this dim opening, named Cygnus X1, located in the Cygnus constellation about 6,000 light-years from Earth. It was many times brighter than the Sun and incredibly dense, with such a strong gravitational pull that not even light could escape from it. Hence, it became known as a dim opening. The nature of dim openings. The idea of a dim opening is both fascinating and terrifying. A region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a dim opening is pulled in, never to be seen again. After discovering Cygnus X1, scientists began searching for other dim openings and found that there might be more than 100 million in the Milky Way alone. Given how incredibly difficult they are to detect, we still don't have an exact number. However, it seems likely that there are millions of dim openings in our universe, making them essential to study. The primary concern with dim openings is their immense gravitational power. Anything entering one is compressed indefinitely until it becomes a singularity. In simpler terms, dim openings are like cosmic vacuum cleaners, sucking everything in. One of the most terrifying aspects of dim openings is that if someone were to fall into one, they would be stretched into a single line, a process called spaghettification. This would happen so gradually that the person would be torn apart before reaching the singularity. So, let's just say no one should ever step into one. Are we in danger? Not really. The closest dim opening is about 500 light-years away, which is far enough to avoid immediate concerns. In 2021, scientists captured the first clear image of a dim opening, specifically the M87 black hole. This image was compiled over several nights, revealing 3 distinct layers to a dim opening. Contrary to popular belief, a dim opening is not just an expanding void of darkness. The first layer is known as the event horizon, the point of no return. Once you pass this boundary, there is no turning back. You will be pulled into the dim opening. The second layer is the photon sphere, where light orbits the dim opening. Any light that enters this region gets trapped by the immense gravitational pull. The third and final layer is the singularity, where all matter entering the dim opening is compressed into an infinitely small point. At this stage, the laws of physics as we know them break down, and we cannot predict what happens next. What makes all of this even more terrifying is that every dim opening studied has been unique. While they follow the 3-layer structure, their behavior varies significantly. Studying dim openings. Because of their nature, scientists cannot study dim openings directly. Instead, they analyze the radiation emitted and the gas and dust surrounding them. Sending a probe, like a Voyager spacecraft, into a dim opening is impossible, as anything that crosses the event horizon is pulled toward the singularity and compressed into nothingness. Despite these challenges, scientists continue to study dim openings through indirect methods. One theory suggests that dim openings form from collapsing stars. When a star burns through all its fuel, it can no longer generate enough energy to counteract gravity, causing it to collapse into a singularity. The mystery of wormholes. To understand dim openings better, NASA scientists focused their research on the center of the M87 galaxy. Astronomers observed a massive, rapidly rotating disk of hot hydrogen gas, moving at an astonishing 1.2 million miles per hour. The only force strong enough to hold this gas in place was a massive object at the galaxy's center, estimated to be 2 to 3 billion times the mass of the Sun, likely a dim opening. However, not all scientists agree. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe a rotating dim opening. He proposed that instead of collapsing into a point, a rotating dim opening might form a ring of fire or a thin circle. Kerr's equation also predicted the possibility of an Einstein-Rosen bridge, also known as a wormhole, a theoretical tunnel through space-time that could connect two distant regions of the universe or even parallel universes. If one were to enter a dim opening, instead of being crushed, they might be funneled through this wormhole and emerge from a white hole in another universe. The concept of space-time. To grasp this concept, consider Einstein's theory of general relativity, which states that space and time are interconnected, forming a four-dimensional fabric called space-time. Objects with mass warp this fabric, creating a gravitational field that affects how other objects move. Imagine space-time as a piece of paper. If you draw two dots on it and connect them with a line, this represents a normal path through space. But if you fold the paper so that the dots touch, this represents a wormhole, a shortcut through space-time that instantly connects two distant points. While wormholes are often considered science fiction, they're a theoretical prediction of general relativity. However, no one has yet observed one. While wormholes remain hypothetical, scientists are actively searching for evidence of their existence. If they do exist, they could revolutionize our understanding of space travel, potentially allowing for shortcuts across vast cosmic distances. However, there are several challenges. For a wormhole to remain stable and traversable, it would require exotic matter, a theoretical form of matter with negative energy density. Without this, the wormhole would collapse almost instantly. Although exotic matter has never been observed, its existence is not ruled out by physics. Even if wormholes exist, traveling through one might be dangerous. Some theories suggest that tidal forces inside could stretch and tear anything that enters. Others propose that a wormhole could connect to different points in time, raising the possibility of time travel. Though this remains purely speculative. Could dim openings be gateways? Some physicists theorize that dim openings could act as natural wormholes. If a dim opening rotates fast enough, it might create a passage instead of crushing everything inside. This idea, called a Kerr black hole, suggests that instead of leading to a singularity, the core of a rotating dim opening could connect to another part of the universe. If this is true, dim openings might not be the destructive endpoints we once thought. Instead, they could serve as cosmic gateways to unknown regions of space or even alternate universes. The future of black hole research. Advancements in technology are helping scientists study dim openings more closely. The Event Horizon Telescope, EHT, a global network of radio telescopes, captured the first image of a dim opening in 2019, confirming many of Einstein's predictions. Future telescopes, such as the James Webb Space Telescope, will allow astronomers to observe dim openings in even greater detail. Scientists also hope to detect gravitational waves, ripples in space-time caused by merging dim openings, which could provide more clues about their nature. What lies beyond? Despite decades of research, dim openings remain one of the greatest mysteries in astrophysics. They challenge our understanding of space, time, and gravity, pushing the limits of what we know. Are they simply cosmic vacuums that swallow everything, or do they hold the key to new dimensions and interstellar travel? Could they be the remnants of ancient universes or the birthplaces of new ones? For now, the answers remain hidden beyond the event horizon, waiting to be uncovered. Directly, wormholes are inherently unstable and would collapse rapidly. The presence of an Einstein-Rosen extension would mean black holes are not just gaudy vacuum cleaners. However, they could also be doors to various regions of space-time. Could we, at some point, use a wormhole to travel through time? Tragically, the answer is likely no, not yet. Even if we could stabilize a wormhole, it is implausible that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can travel through space-time. Despite this, the theory of wormholes and black holes as pathways to different regions of the universe, or even different times, has fascinated physicists for a long time. The possibility of shortcuts through space-time, allowing travel across vast distances or even into the past, could be revolutionary if feasible. The Kerr wormhole, named after Roy Kerr, is one of the most intriguing concepts in this field. It is a theoretical passage through space-time that could connect two distant points, possibly linking different universes or different times within the same universe. The Mutt wormhole is ring-shaped, like the mirror in Alice in Wonderland, where passing through it might transport a traveler to another universe or time with different physical laws. While the possibility of wormholes as a means of interstellar or time travel is fascinating, it is also highly questionable. Some physicists argue that wormholes, particularly Einstein-Rosen bridges, might be unstable or too difficult to traverse due to intense radiation and subatomic forces. Critics point out that Einstein's equations, which describe wormholes and black holes, only account for gravity and not for the quantum forces that govern radiation and subatomic particles. To truly understand these phenomena, a new theory is needed, one that unifies gravity with quantum mechanics. This theory of everything would combine Einstein's theory of gravity with quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on such a theory for decades. The leading candidate for a theory of everything is superstring theory, which unites gravity with quantum mechanics. It suggests that subatomic particles are actually tiny vibrating strings, and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. Superstring theory also explains various strange phenomena by demonstrating that as strings move through time, they warp the fabric of space-time, producing black holes, wormholes, and other extraordinary solutions to Einstein's equations. However, the extra dimensions required by superstring theory are so small that we cannot observe them directly. The most precise measurements in our laboratories only account for the four known dimensions of space-time: length, width, height, and time. But how can we be sure additional dimensions exist? One possibility is that these dimensions are so tightly curled up that they are invisible to us, much like a sheet of paper rolled into a tiny cylinder. If you were a tiny insect walking on the paper, you might not notice the curvature. Similarly, the extra dimensions of spacetime in superstring theory could be curled into tiny loops or spirals, unseen yet influencing the behavior of vibrating strings within them. Another possibility is that these extra dimensions were more apparent in the early universe during the Big Bang. Some versions of superstring theory suggest that the universe initially existed in a 10-dimensional state, with all dimensions equally visible. As the universe expanded and cooled, the extra dimensions folded in on themselves, leaving us with the 4 dimensions we observe today. If this is true, we might still find traces of these extra dimensions in our universe. The mathematics behind superstring theory is incredibly complex and has led to new fields of mathematical study. However, solving the problem of a quantum black hole remains challenging. Many physicists have attempted to do so, but no one has succeeded yet. Edward Witten, from the Institute for Advanced Study at Princeton, has called superstring theory 21st century physics that fell by accident into the 20th century. Last year, some physicists announced a significant breakthrough. Superstring theory could fully solve the problem of a quantum black hole, but only in 2 dimensions, not 10. Many believe it's only a matter of time before someone solves this puzzle. Until then, it's too soon to expect intergalactic or time travel. However, one thing is clear. There are simply too many questions, and even more possible answers. Michio Kaku's work in string theory introduces a fascinating new idea. Perhaps the Big Bang wasn't as big as we typically think. It wasn't an enormous explosion or a chaotic burst of energy. The standard model of the Big Bang doesn't explain what caused the event or how it happened. It merely states that it did. We need a theory that explains what happened before the Big Bang. String theory suggests that our universe may have formed from the collision of 2 separate universes or emerged from another universe, like a child being born from its mother. This connection between universes is known as a wormhole, similar to a tunnel linking 2 bubbles. We may have already found evidence of this umbilical cord connecting our universe to another. In fact, we might already be living inside a black hole without realizing it. Because we exist in 4 dimensions and cannot see beyond them, it's possible that what we perceive as a black hole is actually a wormhole leading to other dimensions. If true, this would fundamentally change our understanding of the universe and our place within it.